Okay, so as mentioned, it's normally a 4-hour lecture that I give to the students of COSCHEM, the Society of Cosmetic Chemists of South Africa, and I have done my best to condense this into around about a 50-minute presentation, which I'll do today. I'm going to try to slow myself down a little bit because I do tend to speak quite fast, and I hope my South African accent isn't too difficult to understand, but yeah, hopefully that'll be okay. Cool. So let's dive right into it. So the topic of today will be surface chemistry. As you all know, is extremely important in cosmetic chemistry. It's not necessarily that important to understand all of the aspects just to make a cosmetic product, but it's certainly beneficial, especially when you run into trouble and you've got some emulsion splitting or you've got some something going haywire. The best way to troubleshoot is actually to understand the science behind it. So that's really where I think these things become important. So the topics that we'll talk about today is going to be the principles that govern the colloidal state in cosmetic science, as well as the forces that exist at these interfaces and the significance of measuring them. We're going to look at adsorption isotherms and monolayers. We're going to look at contact angle in wetting, and we are also going to look at the critical micelle concentration and how all of that works. Okay. So firstly, just to explain, so we're going to first talk about colloidal systems, and I just want to explain what colloidal systems are. And I drew these little pictures to try and explain it. So please don't blame me if these are not on scale, because they certainly are not. But it's my best attempt at trying to explain where colloidal systems fit into the world of surface chemistry. So to understand it, let's first look at true solutions. So true solutions, a typical example would be sodium chloride or salt dissolved in water, just like in the ocean. You're going to have extremely small particles, ions actually, that are going to be completely dissolved in the water phase. And these particles will not be visible with the naked eye at all. These solutions tend to be completely clear, and they tend to be very stable. It's not really going to separate or anything like that. If you think about a salt solution, the real way to separate it would be, I guess, to evaporate all the water out so that the salt actually crystallizes. So very stable solutions. That's on the one extreme. On the other extreme side, you get suspensions. So the little example that I chose in the picture there would be a puddle of mud, for instance. So if you had to go scoop up a bit of that muddy water and you left that to stand on a counter for a while, you will actually see those particles precipitating down and forming a layer at the bottom. And it's because these particles are quite big in size. They are sometimes even visible with the naked eye. They are not that stable. They will ultimately destabilize. And so that will be suspensions. Somewhere in between, you will get colloidal solutions. So colloidal solutions, as you can see in the picture, the size of those particles are somewhere in between that of true solutions and suspensions. And they could have the properties of either of the two. It could be a completely clear solution. It could be slightly opaque or cloudy, I guess. They can be quite stable for a long period of time. They could also be destabilized. And typically these solutions, like I said, can be clear or let's say milky. So the example I chose here is, for instance, milk. I mean, milk is a typical, I would say, an emulsion or a liquid in liquid emulsion. And those are actually colloidal particles inside there. So as we learned just now, colloidal systems or colloidal particles have a size of around about 1 nanometer to 1 micrometer. I mean, there is a lot of different references that will give you all kinds of ranges. When I did my research, I could see that around about between 1 nanometer and 1 micrometer is where the particle sizes of most of these fell. Nothing in the real world is ideal, but in science, we often look at ideal cases just to understand things. I mean, you've got to start somewhere. You've got to look at an ideal case, understand that, and then build from there to understand the real world. So an ideal system, an ideal colloidal system will have 2 phases, and that will be your continuous phase and your dispersed phase. So your dispersed phase would, let's say, be your colloidal particles, and your continuous phase would be the solvent or something that is dispersed into. So because these are extremely small particles, you will have very large surface areas ultimately because these particles are so small. And for that,